Hi everyone. In this lecture, we're going to go over linear equations and integrating factor. So let's first see what a linear equation is. When you have a differential equation written like that, that means a1 of x times dy dx plus a0 of x times y equals to g of x. This equation is said to be a linear equation in the variable y. So again, I have the definition here, which is the same thing. Just remember a1 of x times dy dx plus a0 of x times y equals to g of x, and that's a linear equation. Now, if changing it to standard form, if we divide everything by a1x, every single term, a1x, and this side by a1x. So here dy dx is by itself and we have p of x, but what is p of x? P of x is just a0 of x over a1 of x, so we call that p of x times y, so we have it equals to f of x. But what is f of x? F of x is g of x over a1 of x. So what you want to do is to not have any coefficient for dy dx, so you divide everything by a1 of x, and when you have this form, that's called the standard form, because that's how what we're going to use to solve it. Now, if you look at this, this looks like a product rule of differentiation. So you have dy dx plus a function times y equals to f of x. So just to refresh your memories of the product rule, the derivative of u times v, and I wrote it like that, u v prime is u prime v plus v prime u from calculus, the product rule. However, there exists a function mu of x such that its product to the differential equation the will turn the left-hand side, this side, into a complete product rule. So we are looking for a function. If we multiply that by both sides, so this becomes a complete product rule. So this is v times dy dx is the u prime, and this is v prime times y, which is our u. And of course, the right side is just mu of x times f of x. Now let's see, we said this is the integrating factor, so what's going to happen? So it's that is just mu of x, but what is mu of x times p of x? That's mu prime of x right here. So we can say mu prime of x over mu of x dx equals to p of x times dx. So again, this equals to that. What you can do is divide both sides by mu of x and multiply both sides by d of x. So that's what we get. So then we can take the integral of both sides of that expression. The integral of mu of x, mu prime of x over mu of x, we know that's ln. I can leave this side the same as it is. So that becomes ln absolute value of mu of x and equals to the integral of p of x dx. Now, if you want to solve for mu of x is going to be raised to e, or the base is e here. Mu of x is going to be e to the power of the integral of p of x dx. So our goal is to find p of x, and that's called the integrating factor. So now let's go over this. Since mu of x is equals to e to the power of p of x dx, turns the left-hand side of differential equation to a complete product rule. So now let's see what happens. That's we said mu of x times dy dx plus mu of x times p of x times y equals to that, and that's the product rule. So what is this? Is product rule of what? Of mu of x and y. The derivative of mu of x times y is going to be the derivative of y, which is dy dx times mu of x, plus the derivative of mu of x, which is that, and that's times y, and that's what we get. So now if we integrate both sides, we continue. The integral of that is just mu of x times y, and you take the integral of the right side, and that's how you can write. Then finally you can isolate y, or y of x, dividing both sides by mu of x, and you get that expression. And if you can integrate that, then that's going to give you the solution of the differential equation. Now we have the steps here. Whenever you have solving a linear first order equation, put the linear equation into standard form. That means divide both sides by a sub 0 of x. Then so a sub 1 of x, actually, not a sub 0. So basically get dy dx by itself. So let's go back to the steps. Form the standard form of the equation, identify p of x, and then find the integrating factor, which is e to the power of integral of p of x dx. You do not need to use a constant finding the integrating factor. So when you find the integral of this exponent, do not use a constant. Multiply both sides of the differential equation, the standard form, by the integrating factor. The left side of the resulting equation is automatically the derivative of the product of the integrating factor and y. So again, the derivative of that is just that, so e to the power of p of x dx times f of x. Integrate both sides and you can isolate y. This is an example that's going to make it much easier. Now this is already, we have dy dx minus 3y equals to 0. Dy dx is by itself. Now we want to find p of x. In this case, p of x is -3. So then the integrating factor is going to be to the power of -3 dx. And if you take the integral of that, is e to the power of -3x. No constant needed here, remember. Now we multiply both sides of this equation by e to the power of -3x. So you get e to the power of -3x times dy dx minus 3 times e to the power of -3x times y equals to e to the power of -3x times 0. You know this is a perfect product rule, and this is just the derivative of that and y. So you can write dx of e to the power of -3xy equals to 0. Now to finish this problem, you can take the integral of both sides. So let me just show it to you here, and I wrote it here. So the integral of dx e to the power of -3xy dx equals to 0, the integral of 0 dx. But what happens, that side is just e to the power of -3xy, and the integral of 0 dx, we know it's a constant. So now the general solution, we can isolate y here. So divide both sides by e to the power of -3x, the power of -3x. So then you can take that up and make the exponent positive. So you get y equals to c e to the power of 3x, and x is defined everywhere. So that's the solution. Let's take a look at example number 2. We have x times dy dx minus 4 times y equals to x to the 6 e to dx. Here we notice we have that coefficient. So what we need to do is divide every single term by x first. So isolate that. So that becomes dy dx 4 divided by -4 divided by x is -4 over xy, and x to the 6th power divided by x is x to the 5th power e to dx. This is the standard form. Now we can find the integrating factor. So we know this is, that coefficient is the integrating factors. So if you write e to the power of the integral of px is going to be -4 over x dx. So the integral of dx over x is ln of x. So this is going to be e to the power of -4 ln of x, and that's going to be to the power of ln of x to the power of -4. And we know this is just x to the power of -4. So we have the integrating factors. So we multiply both sides of the equation, this one, the standard form, by x to the power of -4. So you get x to the power of -4 dy dx minus 4x to the power of -5 y equals to x to the power of -4 times x to the power is just x e to the x. So we know this is the product rule of that expression. So the derivative, the way you're going to write that, you can say the derivative of that expression is going to give you x e to the x. So the solution, we have that, and what you need to do is take the integral of x e to the x, and of course you have to use the integration by parts for that, and I have an example. I'll show it to you. So if you do that, you get x e to the x minus e to the x plus c, and then what you can do, initial condition is not given here. Then you isolate y, so divide both sides by x to the power of -4, and that's the solution. So here I put a note, but later on we're going to see x has to be greater than 0 for both functions to be continuous, and x equals to 0 is a singular point. Be patient, we're going to go over this one. So now the next one, example 3, you're given an initial condition. So this is a linear equation, so divide an entirely standard form, and we see that here the coefficient is of y is 1, so our integrating factor is just 1. So if we can write, I kind of solved it here for you, p of x equals to 1, so mu of x equals to e to the x dx, and this is just e to the x. So that's the integrating factor. Multiply both sides by integrating factor, you get e to the x dy dx plus e to the x y equals to x e to the x. And so you know this side is the derivative of e to the x y. So you can say e to the x y is the integral of e to the x e to the x dx. And I did do to refresh your memories of integration bar parts, this is u dv. So u dv, our u is x here, our du is dx, dv, I called it e to the dx dx, and v is e to dx. And you know, integrating by parts, the integral of u dv is u times v minus the integral of v du. So here I wrote e to the xy equals to uv. So u times v minus the integral of v du, and v du is just that times that. So this is easy to integrate. So you get x e to the x minus e to the x plus c. Use the initial condition. We know that y of 0 is 4. Just substitute both sides. So when x is 0, y is 4. So e to the 0 times 4 equals to 0 times e to the 0 minus e equals to c. Solve for c, and you can get c equals to 5. And here you have the curves for different values of c. If c is 0, then we see that we have just a line right here. Now, next one is kind of a piecewise defined function, and we can f of x is that we have to solve it, and we know y of 0 is 0. So that's the initial condition. So it says dy plus y equals to f of x, but f of x is defined here. If x is between 0 and 1, then f of x is 1. If x is greater than 1, then f of x is 0. So let's start with this one. Dy dx plus y equals to 1. This is already standard form, and we know the integrating factor is 1 here, so we just get mu of x equals to e to the x. So the derivative of e to the x y equals to e to the x, multiplying both sides by e to the x, that's what you get. It's done fast, but it's the same thing we used. And then if you isolate y, you get 1 plus c1 e to the negative x. Initial condition, we know y of 0 is 0. So if you substitute when y is 0, x is 0, you can solve for c1. So we get our function y equals to 1 minus e to the negative x, and x is between 0 and 1. If x is greater than 0, then f of x changes. So you get 0, and if you do the same thing, you get c2 e to the negative x. So then you can write it like that. However, y is continuous. If it's continuous, then you know that these two functions are the same when x equals to 1. To solve for c2, you put them equal to each other, but you substitute x by 1. And if you do that, you get c2 equals to e minus 1. So then you can write y of x as 1 minus e to the negative x, and e minus 1 times e to the power of negative x. And the first one, of course, when x is between 0 and 1, and the second one when x is greater than 1. I just want to give you a little lecture here about error function and complementary error function. By definition, error function is 2 over square root of pi, the integral going from 0 to x e to the negative t squared dt, and the complementary error function is ERFC of x is 2 over square root of pi going from x to infinity. So now the error function in reality, a probability is in reality a probability function, which means that the integral over its domain equals to 1. So based on this fact, we can solve for, so if we write this from 0 to infinity, it's 1. So then you can say that if you solve that, then you can say that one is just pi, square root of pi over 2. So now the relationship between error function and complementary function, if you add them, you get 1. And let's see how this works. We have a linear equation here, and then the initial condition is given. So this is standard form. We know this is p of x. So we can say this is e to the power of negative x squared. And if I multiply both sides, not that, but this one, by e to the power of x squared, e to the power of negative x squared, then this is what we get. So then we know this is a perfect product rule. So the derivative of e to the power of negative xy equals to 2e to the power of negative x squared. However, this is not easy to integrate. So we can say, just like the first lecture or the separable variables, we can solve this by using the example 4. So I just brought it here for you to see. So we can say dy dt, the integral of dy dt times dt equals to the integral from 3 to infinity negative t squared dt. Basically, that's what we're using. So let's see how this works. So now once we get that, if we take the integral of both sides, we can use t here. So we can say d over dt e to the negative t squared times y of t dt equals to, on that side, same thing. So we can use that is the same thing as this one. So then the integral of that, if we do that, we know it's going to be e to the negative x squared times y of x minus y of 0. Use the limits to substitute. And then you can use the initial value here. Well, you can divide both sides by e to the negative x. And I just showed it here and isolate, but not the initial. And actually, you can use the initial value because we know y of 0 is 1. So basically, you can substitute that 1 and divide everything by e to the negative x squared. And if you do that, you're going to get this solution. Now from here, we can factor out e to the x squared, and we can take this side and multiply the top and the bottom by square root of pi. And if you do that, this becomes the error function. So another way of writing the solution, you can say the solution is e to the x squared times 1 plus square root of pi times the error function, because by definition, this is the error function. I think that's it for linear equations. Please try some examples from the homework, and I'll solve some examples for you in my next video. Thank you for watching, and I'll see you in the next video. Have a good one.